Oh, that's it. Ah, green. Hello and welcome back to Calculus 3. Today we are talking about lines and curves in space. We start by understanding that the difference between 2D and 3D space. In 2D space, your line is confined to the 2D graph, and everything you learned so far, meaning x squared, sine x, ln x, whatever, those are all 2D lines and curves. Also linear line, right, y equal mx plus b. So all of that stuff is 2D. Now we move to 3D, and we would like to know how we can mathematically describe whatever line in space. And it doesn't have to be a physical object. It could be a path that is traced by a fly or an airplane or a submarine through the water, right? So we want to know how to describe certain things. You know that you can make a spring, right? It's a coil called helix. We want to see equation for that. And then many other lines. In order for us to achieve something like this, we would have to trace each point in three-dimensional space with a vector which stretches from the origin. So if I have some kind of a curve in space, and that sits in a XYZ three-dimensional space, each point of this line, call it L or whatever, is going to be traced with a vector which stretches from the origin to the line. And we actually call that vector R. Stands for radius, right? Now this R is going to adjust. It's going to change its direction and its magnitude to match different locations along this line. So now this R is going to be given as a function of a parameter t, which you can understand if you want to as time. So I'm going to call this R of t, and this R of t is going to be a vector of three functions in time and this we are going to call vector valued function. So now, if I have a vector valued function, say 3t, 2, and e to the t, I can compute that vector valued function at t equals 0 and get that R of 0 is 0, 2, 1. This is a vector which we can draw in 3D space, and using its terminal point 0, 2, 1. We can compute at t equals to 1, get R of 1, which would be 3, 2, and e. T equals to 2 would be 6, 2, e squared, and so on. Now, you can calculate any other value. This is not discrete, right? It's continuous. So you can calculate, 1.5 or 3/2 or pi, whatever. And when you line up all these dots in 3D space, one next to the other, right? Dots meaning the vectors that are pointing towards those locations in space, you can trace the line. So all curves in 3D space are going to be traced by what we call vector-valued function. Now, you can have a vector-valued function in 2D, 3D, 4D, in any dimension you want. So if I go and say that my vector-valued function t is given as t squared, I can compute the chart of values here, right? For t, let's say -2, -1, 0, 1, and 2. And I can get my xy locations, which I can graph. So for -2, we have -2 and 4. Then we have -1 and 1. Then we have 0, 0, 1, 1, and 2, 4. All I did is I placed t one at a time in the vector-valued function, and I came up with these points. You actually come up with vectors, but remember that the vector is pointing towards the terminal point, and the terminal point is whatever is there in the vector. Now, if we graph these guys, we have 0, 0, -1, 1, +1, 1, 2, and 4, and 2, and 4. We are going to get parabola. So this corresponds to your t equals -2, t equals -1, t equals to 0, t equals to 1, and t equals to 2. Isn't this familiar? What is this? You already know this. What are the right words? What does this and this represents? What is it? Collection of parametric equations. Very good. So, technically, your vector-valued function is a collection of parametric equations. As vector is just a collection of numbers or functions. Matrix is a rectangular array of numbers or functions. So you just take a look at what the objects are, and these objects are, in this case, functions which will give rise to numbers as we go on. So now, what do I have? Well, if I want to describe a circle using vector-valued function, I know from Calculus 2 that x squared plus y squared, let's say, equal to 16, circle radius 4. I know from Calc 2, here, Calc 2, I know that the parametric set of equations is 4 cosine theta and 4 sine theta. That's the parametric set. Now, in Calc 3, we write r of t is equal to 4 cosine t, 4 sine t. So it's just a new notation, guys. We are not learning anything new. We learned, well, we did learn new name. So a collection of these parametric equations placed in a vector is called the vector valued function. That's new so far. Wasted 15 minutes of our life, right? To learn 2 words to describe the same idea. So now we use the concept of vector valued functions to describe curves in 3D. So my last 2 examples were 2D, to just make the connection between something that is very familiar to you, the concept you learned in terms of parametric equations, and the new notation that we are using in new words. So now we finally want to work on lines in space, meaning R3, right? You are familiar with the fact that in R2, that's 2D, your line is given by y equals mx plus b. In some sense, the 3D equation needs to mimic this. Most of our Calculus 3 class is going to be an upgrade to what you have learned before. The vast majority of the class is going to be the upgrade to what you have in 2D. So now, if we try to construct the equation for the line, we are going to need 2 vectors. We know that lines are pinned in space if you are able to locate 2 points in space, no matter where they are. As you have 2 points in space, you can strike a line through the 2 points. You can have 3 points in space, but they have to be collinear to hold the same line, right? Because 3 points can also make a triangle. So if the 3 points are collinear, they make a line. So the minimum requirement is 2 points. If you only have 1 point in space, then line can wobble and rotate around that point any way you want. So you can't define a line with 1 point. You can define a line with 1 point and a function, right, which is the tangent line in Calc 1. But then again, you need 2 pieces of information, either 2 points or a point and a function. So you can do the derivative and all that good stuff from Calc 1. So now you see that I have 2 points there, and I am going to stretch 2 vectors to those points. And there will be a vector in between, right, that gives us the direction between those 2 points. So now what I'm going to do is I'm going to fix this point here. I'll call this point P0 with coordinates x0, y0, z0. So that's the one that is fixed. And this is a point P with coordinates x, y, z, which is the one that actually takes on any point along the line L that we are trying to figure out. So now that will give me that this vector r over here is going to be called r0. That's the initial vector. And the other one over here is just vector r of t that we are used to. If you remember the way this formula works in algebra, you have the y-intercept b, and then you then you figure out the slope, and you thread through the y-intercept. So you know where the y-intercept is, you know what the slope is, and then you set the line through that slope. That's with the slope through that point. That's the algebra part. Well, we're going to do the same thing here. I have my point which is fixed in space, all I need to do is to figure out what is the vector, the green vector. We're going to call that green vector vector v. So vector v has to be x minus x0, remember, it's terminal point minus initial point, y minus y0, and z minus z0. So this is a standard way to find a vector when you have initial and terminal points given. Green vector is stretched between points p0 and p, so vector v is actually a vector p0, p. That's what the vector is. And you know that you are supposed to subtract coordinates of vector p, so coordinates of vector p minus coordinates of vector p0 to come up with the vector there. So now what is my vector r? Well, if you take a look at the heads to tail method of addition of vectors, you can see that the vector r, this motion happens in time, so I have to add a t over there, so it's this concept has to, we are calling it vector v because eventually that's going to be the velocity, and that green vector is actually the tangent, and that's the derivative, and see, all of these things kind of fall into place. So if r is the position, the derivative is tangential to it, and it's going to be the velocity, and right, so there's a reason why it's called v. It's not just, oh, we picked right, we could have used u, right? Generally we use u for the vectors. You have the distance plus another distance to give you the final distance. And if you take a look at the heads to tail method, it's red plus green will give you the blue one. So if you observe the equation, it says r of t is equal to r0 plus vt. Well, y equals mx plus b. See that? It's just a vector equation. It has the same form. It must have the same form. Right? But now, the trick is that all of these guys, each one of these, is a vector with 3 coordinates. So, vector r is the vector of x, y, and z. Vector r0 is the vector x0, y0, and z0. And the vector v, well, we just call that ABC. We did not define yet. I mean, I did put x minus x, right, and all that stuff, So now, if I put this in the, if I plug these in, I have that the equation r, x, y, z is equal to x0, y0, z0 plus vector ABC, that's your slope, like the direction vector, times t, parameter in time. And now, I just write equation for x, which is x0 plus at, equation for y, y0 plus bt, and equation for z, z0 plus ct. Yay, parametric set, right? From where? My equation of the line, r of t, actually, go to the next line, I'm going to box it. So this gives us that r of t is equal to, and now as the vector valued function is just, right, the set of these parametric equations. So this equation here is the equation of the line in 3D. This equation here is equation of the line in any D. So this is any dimension equation, any dimension. Linear algebra would write equation that way, because the straight line in 8-dimensional space will have 8 components. So you will have X, Y, Z, and then other 5 letters in there, right, for 8 dimensions. Since we are only dealing with the 3-dimensional lines, we say, all right, let us use this one. So this is line in R3. That's what we have. So line in R3. So the first exercise for you to enjoy is find the equation of the line passing through, and then we pick whatever 2 points, 3, 1, -2, and 0, 4, and 1. There you go. So find the equation of the line passing through these 2 points. Go. And I'll leave the definition. All right, so we are going to make, let's say, this our fixed point, P0. Vector V will be given by 0 minus 3 is negative 3, 4 minus 1 is positive 3, 1 minus minus 2 is also 3. All of these 3's lined up. Now we have that our vector valued function r of t is given as, so we start with x0 plus at. x0 is 3 minus 3t, right? This is your ABC over here in vector v. And these are your x0, y0, and z0, right? So we have 3 minus at, right? So that's that one. Then we have 1 for y0 plus 3t, and finally negative 2 plus 3t. And that gives us the vector. That's too dramatic. There we go, less dramatic. Yes.
What would be the second one of the second zero?
You will compute that and see what happens.
It's not the same. But it's the same amount. It's not the right.
Mm-hmm. Two lines are parallel when? When would two lines be parallel? Mm-hmm. Well, if they have the same vector v, right? Or if vector v is reversed. So two lines are parallel if v1 equals v2 or v1 equals negative v2. They would have the same orientation in space and the two lines would be parallel. Two lines are perpendicular when? Oh, orthogonal. Two lines are orthogonal when? Yeah, but we have a much more powerful tool than that. Yes? Dot product is 0. v1 dot v2. These are all vectors, guys. Is 0. If the dot product of the direction vectors is 0, that means they're orthogonal in space. Great. Curves in space. Again, we are focusing on R3. You know R2. We already talked about it. R2, your x squared, your sine x, your ln x. So those are the curves in R2. You studied that in pre-calculus and calculus. Now we are focusing on R3. Curves in R3 will be described by the vector-valued function R, which is the collection of the parametric equations, and we'll just leave these as FGH, right, in respect to parameter t, or time, because anything can go in here. So we have f of t I, we can also use this notation, plus g of t j, plus h of t k. So curves in space will be just represented with a set of parametric equations, which is why it's important to have to know parametrization. So now, I'll write is that these curves are oriented. And this is going to be important for definitions and theorems in chapter 14. We're not going to use that almost at all until we get to chapter 14. I am going to actually use the simplest way to explain this is obviously to use the 2D case of a circle, where you swap sine and cosine in parametric equations. You swap the direction, the orientation. So I'm going to give that example, but as soon as we cover helix, I will also talk about the direction orientation there. So let's start with the 2D example. So a circle which is oriented counterclockwise will have the set of equations x equals r cosine t and y equals r sine t, giving you the parametric set r cosine t comma r sine t. Now, if the orientation is clockwise, then you have x equals r sine t and y is equal to r cosine t, giving us the r of t to be r sine t, r cosine t. So these are the things that we have in terms of that the curves are oriented. Now, that will be connected to the tangent line, it will be connected to the velocity, right? Velocity is a vector which has direction and magnitude. Magnitude of velocity is the speed, so that's how fast you are going, but velocity as a concept is not just how fast you are going, but also which way, right? So it will include the orientation in that case, right? Because in this case, right, the tangent vector is going towards the left, and in this one, it goes towards the right. So clearly, that's a different direction. We are discussing the orientation because for the two-dimensional object, right, you have already x and a y, which should fully describe the shape, the path, right? Because that's two-dimensional object, and you have two dimensions x and a y. As soon as you involve a third variable or a third, we'll call it parameter, right? In this case, time. Well, that immediately determines whether you have going to the left and going to the right. We have to welcome our Cornell student. Thank God. Anyone wants to transfer to Cornell, talk to this guy. A year of School of Engineering is still alive. So it's possible. Barely alive, but alive. Do what? Cornell, yeah. The first curve we are going to discuss in 3D is the helix. Helix is actually just a spring. You know the spring when you take your pen apart, right? You add a little winding metal wire. So the shape is called a helix. So as you draw the helix first, then you draw the z-axis through the middle of the helix, and then you put your x and y. All right, so I said we are going to use these coordinate systems, right, to suit whatever we have. When you take the helix, right, which would be wrapping around the bottle going up, and you look at its base, it's a circle. So if you look from the top view, you would have your x and y axes at 90 degrees and the z-axis pointing towards your eyes. You see that in the xy dimension, which is the domain of this vector valued function, you will see it's a circle. So we are going to start describing the equation as r of t, and now for x dimension we have r cosine, r again, how about we use rho? Rho cosine t, rho sine t, and then over here I'm just going to leave it as h of t, and I will explain why. First I want to say that, okay, in this case now both of these values are rho. If I have different values for cosine and sine for those rows, if I just have a and b, then it would be ellipse in the base, right? Observe also that the helix in this case is wrapping around z-axis, therefore your circle is in x and y locations. This can wrap around y-axis and your circle would be xz, right? So your sines and cosines will go into x and z location, and the function part would go on y because it's wrapping around y. So hopefully we understand that at the base of the helix, right, at the base of the helix, which is a spring, and you can just set it to stand up on the surface, that base is a circle, and because the surface on which it stands is xy, the parametric equations for the circle occupy those two positions. Now, I left h of t blank because I can put different stuff in there. I can say h of t is equal to 0. If I say h of t is equal to 0, I hope you see that the entire equation collapses to a two-dimensional circle, equation of a circle, right? Which would be just the base. Then I can say it could be any constant, 7 or 15, which would take that circle from the floor because z was equal to 0, and if it's, let's say, z equals to 10, you would take that circle and you would stick it on the ceiling, right? But it's still a circle. Or I can say t. If I say t over here, well, t is the linear increase, right? And now t is going to give, what I actually have here is I have linear growth. That's what I tried to draw. So I have linear growth in z dimension. Because I have a linear growth in z direction, let's say this is 2, okay? Let's say it's 2. The equation for this particular helix would be r of t is equal to 2 cosine t, 2 sine t, and then t. Or it could be 2t, 3t, 5t, you know, depending on how fast you want it to grow in a linear fashion. Now, cosine is in the x location and sine is in the y. This means it winds counterclockwise. So let me write that over here in blood. Too dramatic. Let's do the blue. Since cosine t is in the x spot, I don't know, helix winds counterclockwise. You can make it wind clockwise just by swapping sine and cosine, right? So orientation is important, right? Orientation is important for later, but right now. And then we have the t to linearly grow. I can put t squared. I can put e to the t. I can put anything I want for that other function. Well, not exactly anything, but if I put another trig there, sine or cosine, what it's going to do, it's going to make, what is that called, that thing that you...
Teeter totter?
Slinky, yes, slinky. And you take a slinky and you connect slinky into a donut, but it's a slinky, all right? So if you add another trig function for t. Actually, I think that's maybe, is that the part of the... Yes, it is. Yes, it is. There we go. So in a textbook, you have the slinky. On page 804. So you can see your equation. Here's your helix, cosine and sine, and here's another sine, right? And that's going to give you this slinky. So we are able to define these lines in space, right? By simply by figuring out what the parametric equations are and then simply placing them into the R vector. Call that vector valued function. Let's see. So that's the talk of the helix. This is elliptical helix, as you can see, because there is a 4 and a 1. We see that it winds counterclockwise. Cosine is first, but we also see the arrows, right, which way it rises up. And we see the linear growth, because I don't care what constant. They have 1 over 2 pi as a constant. Whatever it is, it doesn't matter. The spacing between each one of the next of these levels is the same. So it's a linear growth. I am not sure if they actually... here it is. Perfect. Here is the helix that does not have a linear growth. It has exponential, this exponential decay because e to the negative t, but you can see how it goes. This is actually your spring, because you know how it goes busy at first, and then it kind of goes into the linear, and then goes busy again. You would actually have to kind of stagger that you would have to put 3 different mathematical equations. Or actually, no, you can put 2 exponential. No, you can't, because you need a constant growth. So exponential growth turns into the linear growth, turns back into exponential growth to wind the spring. If you are not... Can I do this? Really? Like, this is what, not a single.
Is it same spring or?
New basic spring collection.
Yeah, I see. This word fixes everything. Oh, there is something, but then we get, oh, perfect, look at that. That's exactly what I wanted. Nice. Oh, come on. All right, do we all see? This is the basic spring that you would have in your pen, right? See how it's busy over here? That's your exponential part, turns into the linear part, and then ends up being exponential again, right? So these are, you actually create, this just gave me an idea to create one of the project problems on modeling this. Yeah, why not? I don't think I have time to actually fix it for you guys, but there's always next semester, so yeah. Or maybe I can, but then it's gonna kill my Saturday. We'll see. I have 2 weeks before you guys get 3 weeks. You get what I want to say. That's that. I am not going to talk about limits and continuity of vector-valued function because that's calculus, and the next 11.6, which we are going to cover after the break, is calculus of vector-valued functions. So I'm not going to cover that part of the lecture. Now I will cover it in about 5 minutes. So you have a whole bunch of homework exercises to enjoy. Get the line through those points, figure out the line perpendicular or parallel to the other line, and so on. So just standard algebra examples that you did 5,000 times so far in life, now just translated into R3 language, right, for our parametric. And then you have all of the line segments, curves. Oh, I didn't talk about line segments. Let's just talk briefly about line segments before we go. Line segments. When I write the equation of the line, that line extends infinitely in 2 directions, right? So if I have a line in space, I don't care what kind of coordinate system we have over here. If I have line in space, it goes forever in both directions, right? Now, line segment, so this is just line. Get glass. So, line segments, if we have a line in space, it extends indefinitely in all directions. Now, what I can do is I can say, well, the line is going to start here and end here. Now, this would be a line segment. And for the line segment, we are going to have difference between the two. And this is going to be, again, important in chapter 14. So when you have the line segment, if you have a line which stretches from, let's say, 0 to 3, then you have to figure out, parameter t from 0 to 3, you are going to have a line segment. If there is no mention of any kind of restriction, your line is infinite. So basically, the helix which I have over here is infinite helix. It goes forever down, wrapping z-axis in a negative way to negative infinity in z, and wraps up forever, going to positive infinity, wrapping around z. However, if I bound the t, and I'm going to bound t for using pi's because we have input, right, in sine and cosine there. That will just tell me how many revolutions. If I go 0 to pi, I just get 1 revolution. So it is going to go up, but it's just going to be 1 winding of the helix. So we'll start and it will go up and it will stop. It's very difficult to draw that. So that would be t between 0 and 2 pi. But then I can have it wind twice, right? If I have it wind, actually, right there. If I have it wind twice, 0 less than t less than 4 pi. So there will be 2 windings of the coil. So if I specify t and it cuts off the negative infinity to infinity, you are getting a segment. It's creating a finite object. If t is not bounded, then it's infinite and a line. So line, segments, helix, whatever you get, it doesn't matter what kind of function it is. It's just, guys, it's just, you know that these lines are just collections of multiple functions. Now, the beautiful thing about education today is that you can explore all of this on a software. Software will plot whatever you toss in. So, you know, use your favorite graphing utility, like computer utility, right? So whether it's Mathematica, or you can use Wolfram Alpha, or whatever other thing you have. And then just, you know, put some random stuff and see how the functions that you put in correlate with what you see back on the graph. That's the only way to learn this. There's nothing that I can teach you in this case. You actually have to explore. There are infinite possibilities. So forget about learning case-by-case basis. Yes, you are going to learn linear line and helix. Those are the 2 basic cases, right? But then there is another infinity of other possibilities following that. So how about you involve maybe 2e to the t's and see what happens there, you know, and a linear function. And then also swapping these and seeing which way they wrap around. So for helix, you put t around x, around y, around z, and you see that it wraps around x-axis, and then around y, and then around z. So these are all learning experiences which you couldn't do just 10 years ago. You couldn't do these things because the software wasn't available. Today, you can spend, you know, an hour or so in front of the screen, just, you know, placing anything in between these commas and see what you get on the other end. All right, let's hit the break and then talk about calculus.